A wire has both elastic and plastic properties. When it is slowly loaded, its extension varies with load as shown by line OXY. So this the removal of the load is represented by the line YZ. This creates area PQ and R on the graph. He says which area represents the maximum elastic potential energy stored in the wire. It looks to be a memory question. The topic is deformation. Yes. Do you suggest anything? It's I shade the area.
Will it be P?
One is this area. Do you remember this area which I'm shading? This is the area which is the energy which cannot be recovered during the deformation. So this is the area which shows with the energy which cannot be recovered. He says the maximum potential energy stored. The unloading means that you have removed the deforming force and the object is being deformed, returning to its original position. What about R? What is R? What is Q? Let's talk about it as a memory.
The R will be the unloading part of it, like where the stress becomes less.
Uh, Q is equal to energy which cannot be. What is Q? What is R? Now, what is P?
Like the energy used to stretch the string.
Hmm. Acha. And Q, what is Q? Q is the energy of Q plus R, and what is R?
R will be the energy which can be recovered.
Good. And the P is the area above the axis, which means the P cannot be our option because he's asking for maximum energy, which is stored in the wire.
So that will be Q plus R.
Q plus Q is the energy which is not stored, which is lost. Just like when you stretch something or when you deform something, some energy becomes heat, some energy converts into sound, which is not stored, which is gone, which is lost. It is part of total energy, but it is not part of stored energy.
Okay, so we are supposed to see the stored energy in this one.
He says stored energy, which is stored in the system.
So Q can't be an option. So B and C will be cut. So it's
Yes.
either P or R.
Yes, correct. Very good judgment. And the problem is P. P cannot be the answer because the concept of area is half or function as an area. It's load extension graph. So load extension graph, area should be in touch with extension. It's a load extension graph. Area should be with extension graph. It is just like when you say distance time graph, the area shows a distance travel when you make a graph of speed against time, but the area should be in touch with time. It's a very technical concept that all areas do not show work done. For when you write the formula is F is equal to Kx or Ke. F is equal to Ke. So that is why area should be with the extension axis. If you want area to become, stored energy. A scientist is investigating the properties of a new material. She plots a force extension graph for the material up to its breaking point. Now, can you tell me that if you see the graph, the area under the graph P to R is the strain energy stored in the material. The area under, this is, remember that this is according to Hooke's law. It should be considered that strain energy stored. Area under the graph from P to R is the work done in stretching the spring. The material stretch elastically from Q to R. It's wrong because we know Q to R is plastic deformation. Elastically from P to Q, this is also wrong. Now, the two options are remaining, which are very close until you have a good understanding between the difference. So they are very close. The wire under the graph, the area under the graph from P to R.
So will it be work done because it is the same like touching the extension?
But the judgment is right, but we should explore it further for our memory clearance, that why it is not strain energy. If I consider this total area, this is the total area. So why we should not say it is the strain energy stored in the material? Actually, the graph they have shown us is called loading. This is the loading graph, and I want you to look again on this previous sketch. This is called loading and unloading. Now, this is a very technical concept to remember, that area under the loading graph is the work done, is the total input energy. It can't be, it is not necessary that it is the strain energy stored. A metal cylinder is able to withstand a compressive force of 4 kilonewton without deforming plastically. The cylinder has cross-sectional area A and would be at its elastic limit when a stress sigma is applied. What is the possible pair of values for A and sigma? He has given us force 4 kilonewton without deforming plastically. It means that this should be the force for elastic deformation, 4 kilonewton. So what is the possible pair of values? I don't have any other information, interestingly, no other info, only 4 kilonewton, but he has shown two forces of 4 kilonewton. It's a compressive case.
So the stress will be force over area, and
Perfect. Stress is equal to force upon area. So I think we can try it by trial and error, because we have the force. So we can say that force is equal to stress is equal to force upon area. So let's make force the subject.
so force will be stress into area.
And we should see and we know force is given.
And Pascal will take at 10 power
So
6.
we should try all the option, like it's megapascal. So I've showed the first working. So please solve this for me.
750.
Sorry, I couldn't get, what did you say?
750.
7.
Yes. The second one is 1200. The third one, C, is 3750.
Sorry, the third one is
3750. And the last one is 6000. So will we take C as it is the closest?
what did you say for the last one?
6000.
No, that's a problem. Actually, no one is coming in this range. We have either we should see our calculation again, or six thousand. But how we take 6,000 or 3750 is looking to be the closest. But the
I
problem is that there are
same.
two forces of 4,000. Did you check the calculation again?
Yes, it's coming the same.
That's strange. Maybe some typing error here, because four kilonewton, so they are getting two forces. No answer is actually coming. The closest we can take is C, which is 3750. But let me see if I can check this question back after the class, and we can save the time, because it's not matching directly. Forces are applied to the ends of a rod that its length increases. The variation with load L of the extension of the rod is shown. Now, remember this concept. It is extension on y-axis and load on x-axis. It's a very tricky concept to remember, that when you say area, it's very important to remember that area should be taken from what axis. By rule, it can be the same, but it's necessary that who is the variable on x-axis and which variable is on y-axis. This is a question in that regard. So as I mentioned again, that work done during the area
So work done should be towards the extension axis.
yes, area is equal to work done Now, this is a technical concept that area should be
So will option A be wrong like that?
because A cannot be the answer. A is coming with load. The area is touching load. B can be the option or C can be the option.
So do we take the total area, right?
No, for that you have to read the question. Forces are applied to the ends of a rod so that its length increases. The variation with load L of the extension of the rod is shown. That point P is the elastic limit, which shaded area represent the work done during the plastic deformation.
Okay, so it will be a portion of it, not the whole area.
Because the word is this. I have rejected A and D because area is touching with load axis. It's a very important concept of mathematics that area is not alone to be judged for a physical quantity. You also have to see that which axis is in contact. So when you say area is equal to load and extension, it's a load extension graph, but they have made extension load graph. So if you see this graph and now you see down, B or C?
Will it be C?
Yes. In an experiment to measure the Young modulus of a metal, a wire of the metal of diameter 0.25 mm is clamped. In an experiment to measure the Young modulus of a metal, a wire of the metal of diameter 0.25 mm is clamped as shown. Scale, marker, wire, clamp, pulley. The wire passes from a clamp around a frictionless pulley and then to a second frictionless pulley where load F are applied to it. A marker is attached to the wire so that the total length of the wire between the clamp and the marker is initially 3.7. Where is 3.7? Total length of the wire between the clamp and the marker. Acha, between the clamp and the marker is 3.7. Scale is fixed near to this marker. The graph shows how the reading on the scale varies with average. I made a very complicated diagram actually. And as you keep on adding the load, it is an extension. It looks to be marker position on a scale. It should be initially it is 4 point something. But why is saying 3.7? Acha, 3.7 should be the initial length. I think 3.7 is the unloaded length. So then when it becomes 4 point something, when it goes on, what is the Young modulus of the metal? What is the formula for Young modulus?
Stress over strain or FL over A.
Very good. Stress.
But in the graph, it is showing like almost 4.7 at 0 Newton force.
4.7 or something. It means actually it is not a marker position. He is not showing the length. It's showing marker position. Now, this is the formula. If you have to read the question again, I think you should read the question again because this story is actually giving a confusion.
Okay, so we'll take the area as pi 0.25 square over 4 and the length as 3.7.
Hmm.
And we can choose any extension from this because it's a
No,
straight line.
I think the y-axis is not extension. We need to subtract it because otherwise the initial length is 3.7. So the wire passes from a clamp around a frictionless pulley and then to a second frictionless pulley where loads F are applied to it. A marker is attached to the wire. A marker is attached to the wire so that the total length of the wire between the clamp and the marker is initially 3.7. So if I start moving from the clamp and I walk till if I walk till the marker, it is 3.7. So it means if I start from here and I reach up to here, this length is 3.7. Okay. And the graph is interestingly showing at zero load, the graph is showing around 4.6 or something like that, or maybe 4.7.
Like if we take 10 as the force, we will minus 8 with the 4.6.
This is the possibility. And now we should see how we can find what is the Young modulus of the metal. So either we go for a concept of gradient, but it is not an extension load graph. It is a length load graph. So we should see the thing because it's not simple to read the graph. It's not a perfect graph. So when they start adding the load, the wire will stretch downward and the marker will move to the right. So should we try from the gradient approach or what should we do? We can try for gradient of this graph. Young modulus can be if we take load. The load is a measure of stress and the extension is a measure of strain. So what if we try the gradient?
The gradient is coming as 0.33.
0.33.
Yes. No, I did it wrong. I think I didn't take it as millimeter. It is 3.3 into 10 to the power minus 4.
No, but that doesn't match with anything. I should draw it again here. Look, this graph is now leading for extension. Initial extension would be 0. I have drawn a line exactly parallel to it. And we should first find the gradient and then reciprocate it